Silence. 17 miles of tunnel coiled beneath the Swiss-French border. A machine heavier than the Eiffel Tower, cooled to a temperature colder than outer space. It fires protons at 99.99% of the speed of light and slams them together roughly 1 billion times per second. Each collision crushes energy into a space smaller than a proton. For a fraction of an instant, the impact recreates the conditions that existed in the first millionths of a second after everything began. Particles that have not existed since the birth of the cosmos flash into being, live for less than a trillionth of a second, and shatter into fragments. Detectors the size of apartment buildings catch those fragments. They measure the angle of every shard, the energy of every trace, the lifetime of every ghost that flickered through the collision point. You do this 1 billion times per second for months, and you build a picture so sharp that you can predict the outcome of the next collision before it happens. Physicists did this for decades. Every prediction held. The accuracy reached 11 decimal places. If you predicted the distance from New York to Los Angeles with that precision, you would be off by less than the width of a single atom. Some physicists stopped looking for surprises. The equations had swallowed everything the machine could throw at them. Then, around 2021, the detectors started returning numbers the equations could not produce. Not explosions of impossible particles, not dramatic failures. A quiet tilt. Certain measurements sliding away from the predicted values by fractions of a percent. If the tilt had been random, you could have ignored it. But it was not random. It appeared in the same measurements. It leaned in the same direction. It showed up in run after run, month after month, and it never corrected itself. The physicists recalibrated the instruments. The tilt stayed. They rebuilt sections of the analysis from scratch. It stayed. They changed the statistical framework. It stayed. You know what a hairline crack in a foundation wall looks like. You press your finger to the concrete and feel the gap. It is too small to matter, but every spring, when you check it again, it is a little wider. That is what the data looks like right now. When physicists confirm a prediction, they hold press conferences. When they find a crack, they cannot explain, they go quiet. Right now, they are very quiet. They are quiet because the crack runs through the most successful theory ever built. 3 generations of physicists hammered the standard model of particle physics together over 50 years. It maps every particle, every force, every way matter and energy touch each other across the observable universe. It predicted the Higgs boson 2 decades before any detector caught it, and when CERN finally pinned it down in 2012, the mass landed within 1% of the prediction. Engineers trusted that prediction enough to bet the machine on it. They used the standard model to calculate how much radiation the tunnel walls would absorb, then poured the concrete to that spec. If the model had been wrong by 0.5%, the walls would have failed, and the collider would have cooked itself from the inside. The concrete held. The model held. Everything held for so long that the map and the territory became the same thing in the minds of the people who used them. You stop questioning a clock that has never lost a second. You set surgeries by it. You launch rockets by it. You build your entire civilization on the assumption that the next tick will land exactly where the last one did. And then, one morning, you notice the second hand dragging. Not by much. Not enough for anyone else to see. But you built a machine precise enough to count the microseconds, and the microseconds are off. The clock still looks fine from across the room. The tick still sounds right. But something inside the mechanism has shifted, and you cannot see what, and you do not know if it is getting worse. That is the standard model right now. The predictions still hold for most of what the collider produces. But in specific corners of the data, in the places where the machine pushes energy to its highest concentrations, the map has started to peel away from the ground beneath it. The ground moved. The map did not. The ground shifted first under a particle called the B meson. It is unstable. It lasts about 1.5 trillionths of a second, and then it falls apart into lighter pieces. The standard model predicts exactly which pieces, Exactly how often, exactly at what angles. The LHCb detector was built to watch this process with a precision no other instrument on Earth can match. When a B meson falls apart, it can produce either an electron or a heavier relative called a muon. The force driving the decay is blind to mass. It does not know the muon is heavier. It should produce electrons and muons at the same rate, 50-50, no preference. The detector found a preference. Slightly more electrons, slightly fewer muons. You run the experiment once and the tilt could be noise. You run it 100 times and the tilt has not moved. You run it 1,000 times and it is still leaning in the same direction, still favoring electrons, still refusing to scatter the way noise scatters. Something was pressing its thumb on the scale. The thumb did not belong to the standard model, and the pressure pointed somewhere specific. It pointed at time, because there was an older version of this tilt, one that James Cronin and Val Fitch had caught 60 years earlier. In 1964, they proved that matter and antimatter do not mirror each other when you reverse the flow of time. The equations demanded perfect symmetry. The particles broke it. The universe had a preference for one direction of time over the other. A tilt so slight that it took a Nobel Prize just to measure it. The standard model absorbed that tilt. It filed the asymmetry under a specific mechanism and moved on. But the new data from LHCb is pouring more asymmetry into that container than it was built to hold. The tilt Cronin and Fitch found in 1964 and the tilt LHCb is finding now are not two problems. They are the same fracture measured 60 years apart. It is deeper than it was. And the fracture does not stop at B mesons. Deeper in the collision records, spread across years of data from two independent detectors named Atlas and CMS, something stranger is happening. It flickers. Since roughly 2015, both detectors have periodically caught bursts of excess events at specific energy levels. More particles coming out of certain collisions than the standard model says should exist. They show up on graphs as bumps. A bump means something appeared at an energy where nothing should appear. If a bump crosses a statistical threshold called 5 sigma, less than 1 chance in 3.5 million that you are looking at noise, you have a discovery. These bumps climb to 3 sigma, sometimes 4, close enough to see. Then they sink back down with the next round of data, only to reappear months later at the same energy. A bruise that heals and comes back in the same spot is not a bruise. It is a sign that something underneath the skin keeps breaking. The safe explanation is statistics. Search through enough energy ranges, and you will find occasional bumps by chance alone. True, but chance does not come back to the same address. Chance does not synchronize across two machines built by different teams in different caverns under the Alps. You are looking at the B meson tilt that refuses to scatter, a time asymmetry that has been growing for 60 years, and bumps that keep flickering at the same energies in two independent detectors. Every one of them involves how particles behave across time, not across space, not across distance, across time. Every one of them gets stronger the harder the collider pushes. Every one of them sits at energies where the conditions begin to resemble the first moments after the universe was born. Something about time at those energy scales does not work the way you were taught. You were taught wrong. 300 years you built everything on a single assumption about time. Isaac Newton wrote it into his equations as a constant, a universal metronome, same tick everywhere, for everyone, regardless of speed or gravity or the mass of the nearest star. Bridges stood on it, cannons fired on it, ships crossed oceans using math that assumed every clock in the universe kept the same beat. In 1905, a 26-year-old pattern clerk in Bern proved the assumption was broken. Albert Einstein showed that time stretches when you accelerate. It compresses when you sit inside a gravitational field. Move faster, and your clock runs slower than the clock of someone standing still. Sit closer to something massive, and your clock drags behind the clock of someone further away. You use this fact every day without knowing it. The GPS satellites circling the Earth right now carry atomic clocks that tick faster than the clocks on the ground beneath them. Faster by 38 microseconds per day. If the software did not correct for that gap, your phone would place you 11 kilometers from where you actually stand before lunch. Every time you follow directions on a screen, you're relying on the fact that time moves at a different speed in orbit than it does in your pocket. Time on the roof of your building runs faster than time in the basement. The difference is too small for your nerves to register. It is not too small for a cesium clock. Einstein did not just prove that time bends, he proved that time is a physical thing. It responds to mass and velocity the way a sheet of rubber responds to a fist pressing into it. It deforms. It has shape. And if something has shape, you can look at the whole shape at once instead of experiencing it from inside one point. Einstein's teacher did exactly that. And what he saw broke everything. Hermann Minkowski took Einstein's equations and rebuilt them as geometry. He fused time and space into a single four-dimensional object. Not time running alongside space, one object. 4 coordinates, length, width, height, and time, woven so tightly that pulling them apart breaks the math. He called it space-time. In this geometry, time is not a flow, it is a direction. You can point north, you can point up, you can point toward next Thursday. Mathematically, those are the same operation. And that is where everything you think you know starts to collapse. If next Thursday is a direction the way north is a direction, then next Thursday is a place. It exists, not will exist. Exists right now at a specific set of coordinates, the same way a city on the opposite side of the planet exists right now even though you cannot see it. You cannot see it because you are in the wrong place, not because it is not there, and everything behind you still exists too. Yesterday did not dissolve. Your 10th birthday did not vanish. They sit at their own coordinates in the block, fully intact, as real as the ground you are standing on. You have been thinking of your life as a journey, a line moving from past to future. Minkowski's geometry says it is not a line. It is a tunnel carved through solid rock. The entire length of it already exists. A worm inside an apple feels like it is crawling forward. Cut the apple open and the tunnel is already there, every inch of it, from entrance to exit. The worm is not creating the path by moving. The path is the shape of the worm, and the worm only experiences it as movement because it is trapped inside and cannot see the whole fruit. You are trapped inside. Your life is not a sequence of moments happening one after another. It is a fixed shape inside a frozen structure. The sensation of moving forward is something the shape produces because it can only read one cross-section at a time. You are not going anywhere. You have never been going anywhere. But you do not feel frozen. You feel like you are moving. You remember yesterday, and you do not remember tomorrow, and something about that difference feels so fundamental that it seems insane to question it. Carlo Rovelli questioned it. Rovelli is an Italian theoretical physicist who spent 30 years working on quantum gravity and came out the other side with an answer that sounds like it was designed to keep you awake at 3 a.m. Time is not fundamental. It is not built into the fabric of the universe the way space is. It is not a coordinate, not a dimension, not a direction. It is a story your brain tells itself, because your brain is broken in a very specific way. Here is what Rovelli means. The equations of quantum mechanics and general relativity, the two deepest descriptions of reality we have, do not contain a variable for time in the way you experience it. They describe relationships between things. This is correlated with that. This state is entangled with that state. But they do not say which came first. They do not have a before and after. The before and after is something you add. You add it because your brain is a thermodynamic engine running on chemical gradients, and chemical gradients only flow in one direction, from concentrated to dispersed, from ordered to disordered, from a sugar cube dissolving in water to the sugar spread evenly through the glass. You cannot undissolve the sugar. Your neurons cannot unfire. Your memories only form in the direction of increasing disorder, which is why you remember the past and not the future. Not because the past is fundamentally different from the future, because your hardware only writes in one direction. A camera that can only record and never rewind will convince itself that the world only moves forward, but the world is not moving. The tape is just stuck on play. Rovelli says time is what ignorance feels like from the inside. If you could see every particle in the universe and track every interaction simultaneously, the distinction between past and future would vanish. There would be no flow, no direction. No before, just a web of correlations hanging in silence. You experience time because you're too small to see the whole picture. The flow is not in the universe. The flow is in your blindness. That should scare you. But there is a version of this that is worse. Lee Smolen disagrees with the Rovelli on almost everything. Smolen is a Canadian theoretical physicist who has spent his career arguing that time is not an illusion. It is the opposite. It is the most real thing there is. More real than space. More real than matter. More real than the laws of physics themselves. And that is the part that should keep you up at night. Because if Smolen is right, the laws of physics are not eternal. They did not exist before the universe, and they will not exist after it. They were born with the Big Bang the same way stars and galaxies were born. And like stars and galaxies, they change. They evolve. The speed of light might not have always been what it is now. The strength of gravity might shift over trillions of years. The rules that hold your atoms together are not carved into the bedrock of reality. They are weather. They are conditions that happen to be stable right now. The way the climate of the Earth happens to be stable right now. And like the climate, they could tip into something unrecognizable without warning. Rovelli says, time is an illusion produced by your limited perspective. That is uncomfortable, but it is static. Nothing changes. The block just sits there. You are frozen inside it. Smolen says the block does not exist. Time is real, time is fundamental, and because time is real, nothing is permanent. Not the constants, not the forces, not the architecture of atoms. You are not frozen inside a safe, unchanging structure. You are riding a wave that is reshaping itself as it moves, and you have no guarantee that the shape it takes tomorrow will support the chemistry that keeps you alive. The question the data at CERN is forcing into the open is which one of these men is right. Is time the frozen structure that Minkowski described, where everything already exists and nothing truly changes? Or is time the only real thing, the engine underneath everything, rewriting the rules as it runs? Either answer breaks something you need. One takes away your future. The other takes away the ground. Both of those answers live in the large-scale world. Relativity, cosmology, the behavior of space and time across billions of light years. But the anomalies at CERN are not large-scale. They happen inside a space smaller than an atom, at durations shorter than a trillionth of a second. To understand what is going wrong at those scales, you have to look at the other half of physics. The half that has been screaming something impossible for 100 years while everyone pretended not to hear. In 1801, a British scientist named Thomas Young set up the simplest experiment in the history of physics. He took a beam of light and aimed it at a barrier with two narrow slits cut into it. Behind the barrier, he placed a screen. If light were made of particles like tiny bullets, you would expect to see two bright bands on the screen, one behind each slit. Young saw something else. He saw an interference pattern, alternating bands of bright and dark, the kind of pattern you get when two waves overlap and reinforce or cancel each other. Light was a wave. That settled the question for a century. Then, in the early 1900s, physicists started running the experiment with individual particles, one electron at a time, fired like a bullet at the two slits. A single particle cannot interfere with itself. A single particle should go through one slit or the other and hit the screen in one spot. It did hit the screen in one spot. But when you fired thousands of single particles, one after another, the spots they left on the screen built up into the same interference pattern. Bands of bright and dark. Wave behavior from individual bullets. The only way to produce that pattern is if each particle went through both slits simultaneously. Not half through one and half through the other. The whole particle through both. At the same time. You are not looking at a trick of statistics. You are not looking at a flaw in the equipment. You are looking at a single object occupying two positions in space at the same moment and interfering with itself on the way to the screen. This is not an edge case. This is not a special condition that only happens in exotic labs. This is how reality works at the smallest scale anyone has ever measured. Every particle in your body did this before it became part of you. It is still doing it. If that disturbs you, you're in good company. It disturbed Erwin Schrödinger so deeply that he designed a thought experiment specifically to prove it could not be true. Schrödinger was one of the architects of quantum mechanics. He wrote the central equation. His name is on the math that predicts how particles behave. And he hated what his own math was telling him. So in 1935, he proposed a scenario. Put a cat in a sealed box. Inside the box, place a device linked to a single radioactive atom. If the atom decays, the device releases poison and the cat dies. If it does not decay, the cat lives. Quantum mechanics says the atom, before anyone checks, is in both states at once. Decayed and not decayed. Superposition. But the atom is linked to the device and the device is linked to the cat. So the math says the cat is also in both states, alive and dead, simultaneously. Schrödinger meant this as a reductio ad absurdum. He was saying, look how ridiculous this gets when you scale it up. A cat cannot be alive and dead at the same time. Therefore, the theory must be incomplete. 90 years of experiments proved him wrong. Every test physicists have thrown at superposition has confirmed it. The cat is not a paradox. The cat is a description of what reality actually does when you are not looking. And in 2022, the Nobel Prize in Physics went to a man who proved something even stranger. Anton Zeilinger spent decades running experiments on pairs of entangled particles. Two photons created together, then separated. Sent to opposite sides of a laboratory. Then opposite sides of a city. Then opposite sides of the Canary Islands. When you measure a property of one particle, the other particle instantly takes the corresponding state. Not after a delay. Not after a signal traveling at the speed of light. Instantly. Regardless of distance. John Bell had already proved in 1964 that this could not be explained by hidden information carried inside the particles. There was no secret code. There was no pre-arranged agreement. The correlation was real. It was immediate. And it violated every intuition you have about how separated objects should behave. You are not looking at two particles communicating faster than light. You are looking at 2 points in space that are not as separate as they appear. The distance between them is not what you think it is. So superposition is real. Entanglement is real. Particles exist in multiple states and remain connected across distances that should make connection impossible. You already know the objection. You have been thinking it for the last 5 minutes. This is the quantum world. Photons, electrons, objects so small that a single molecule looks like a continent next to them. None of this applies to your world. Your coffee mug does not exist in two places. Your car does not entangle with your house. There is a boundary between the quantum and the classical, between the strange and the normal, and you live safely on the normal side. That is the most comforting idea in modern physics. It is also wrong. In 1999, a physicist named Marcus Arndt and his team in Vienna fired molecules of carbon-60 through a double slit. Carbon-60 is not a photon. It is a molecule made of 60 carbon atoms arranged in the shape of a soccer ball. It is enormous by quantum standards, and it produced an interference pattern, the same pattern the single electron produced. The same pattern that means the molecule went through both slits at the same time. The whole molecule, 60 atoms, through both slits. Since then, the record has been broken again and again. Molecules of over 2,000 atoms showing interference. Mechanical oscillators cooled to near absolute zero entering superposition. The LIGO gravitational wave detector, an instrument with mirrors weighing 40 kilograms, registering quantum noise. Quantum behavior in a 40-kilogram object. The boundary between quantum and classical is not a wall. It is a fence that physicists keep pushing further back, and every time they push it, they find more quantum on the other side. No one has found the point where quantum stops and classical starts, because that point does not exist. There is no border. There is no safe side. The quantum world is not a separate reality that operates under different rules down at the bottom of the size scale. It is the only reality. The classical world you experience, the solid, stable world of coffee mugs and car keys and concrete floors, is what happens when the quantum world loses something. Something leaks out of the system, and the strangeness fades, and everything starts behaving the way you expect it to. The question is, what leaks, and where it goes. What leaks is information. A physicist named Wojciech Zurek spent 30 years figuring out the mechanism and gave it a name. Decoherence. Here is how it works. A particle in superposition, existing in multiple states at once, is not fragile in the way you might expect. It does not need a conscious observer to collapse it. It does not need a scientist pointing a detector at it. All it needs is contact. The moment a particle in superposition touches anything, a photon bouncing off a surface, a stray molecule of air, a vibration in the ground beneath the experiment, information about its state starts spilling into the environment, not all at once. It bleeds out. Each interaction carries away a tiny piece of the picture. One molecule of air bumps the particle, and now that molecule carries a trace of which state the particle was in. Another molecule bumps that molecule, and the trace spreads further. Within a fraction of a second, the information has bled into so many surrounding particles that no instrument you could ever build would be able to gather it all back together. The superposition is not gone. It has not been erased. It has been diluted into the environment so thoroughly that from where you stand, it is unreadable. You are sitting in a car with the radio dial locked to one station. The other stations did not shut down. They are still broadcasting. The waves are passing through the car right now, through the dashboard, through your hands on the wheel. You cannot hear them because the dial is locked, and you do not have the tools to unlock it. Decoherence is the lock. It does not destroy the other states. It does not choose one outcome and eliminate the rest. It spreads the rest so thin that you lose access. The mug on your table is in superposition right now. Every particle in it is doing what the electron did at the double slit. But the mug is in contact with the air, the table, the light in the room, and the information about its other states has bled into trillions of environmental interactions faster than you could ever track. You see one mug because you only have access to one channel. That is what Zurek proved. And that is what Zurek could not explain. Because if the other states are not destroyed, if they are only hidden, then they are still running somewhere. Every other version of the mug, every other version of the particle, every other version of the outcome, they did not disappear. You just lost the signal. One physicist answered that question 70 years ago. Nobody listened. Hugh Everett III was a graduate student at Princeton in 1957. His advisor was John Wheeler, one of the most respected names in physics. Everett looked at the equations of quantum mechanics and noticed something that should have been obvious, but that everyone had been trained to ignore. The math did not contain a collapse. Nowhere in the Schrödinger equation was there a rule that said superposition ends when someone looks. That rule had been added by hand, bolted onto the framework by Niels Bohr and the Copenhagen School, because without it the equations produced an uncomfortable result. They produced branches. Every quantum event that could go more than one way went every way. The electron that could pass through the left slit or the right slit passed through both, and the universe split along the seam, not into two copies of the whole cosmos floating side by side. into two branches of a single structure, each one real, each one containing a version of the experiment with a definite outcome, each one invisible to the other because decoherence had bled the information between them into noise. Everett did not add anything to the equations. He subtracted. He removed the collapse rule that Bohr had inserted, and without it the math worked cleaner. Fewer assumptions, fewer special cases. Just the Schrödinger equation running without interruption, and the branches falling out of it like cracks spreading through glass. Wheeler loved the work. He also knew it would end Everett's career. He was right. The physics community dismissed the thesis. Bohr's camp refused to engage with it. Everett published a shortened version, received almost no response, and left academia permanently. He took a job with the Department of Defense doing operations research. He never published another physics paper. He died in 1982 at the age of 51. His son found the body. 30 years after the thesis was buried, physicists started coming back to it. Not because they changed their minds about Everett, because the experiments kept confirming what his math predicted. The branches were not a philosophical interpretation. They were the default output of the most tested equation in the history of physics. Everett did not invent parallel realities. He stopped pretending they were not there. But a dead physicist's math is not proof. You need a machine. David Deutsch built the argument for that machine in 1985, and it took the world 30 years to catch up. Deutsch is a British-Israeli physicist at Oxford who asked a question so simple it sounds like a trick. If a quantum computer can solve a problem that would take every atom in the observable universe longer than the age of the universe to solve by classical means, where is the computation happening? Not metaphorically, physically. Where are the operations being performed? A classical computer solves problems one step at a time. If a problem has 1 trillion steps, the computer takes 1 trillion steps. A quantum computer does not work this way. It places its qubits in superposition, which means each qubit exists in multiple states simultaneously, and then it runs the calculation across all those states at once. The result is not faster processing in the way a faster car covers the same road quicker. It is processing that could not happen in a single universe. There are not enough particles, not enough time, not enough physical resources in the entirety of observable space to perform the computation classically. But the quantum computer performs it. It gives you the answer. The answer is correct. So where did the work happen? Deutsch says the work happened in the branches. The qubit in superposition is not doing two things in one universe. It is doing one thing in each of two branches, and the branches share the result through interference before decoherence separates them. The quantum computer is a machine that reaches across the boundary between branches and borrows computational power from versions of itself that you cannot see, cannot visit, and cannot communicate with except through this one narrow channel of quantum interference. It is not a theoretical argument. Quantum computers exist. They solve problems. They produce correct answers to questions that the resources of this universe alone cannot answer. Every time a quantum computer runs, it is drawing on something outside the visible world. You can call that something whatever you want. Deutsch calls it what the equations call it. Other branches of reality, doing the math you cannot do alone. You might still be looking for an exit. Maybe the branches are a convenient fiction. Maybe the quantum computer works for reasons nobody has figured out yet, and the branches are just a story physicists tell to make the math feel intuitive. Sean Carroll would tell you to look at it the other way around. Carroll is a theoretical physicist at Johns Hopkins, and one of the most visible defenders of Everett's framework in modern physics. His argument is not that branches are the best interpretation. His argument is that branches are what the equations produce when you do not add anything extra. The Schrödinger equation evolves the quantum state forward without interruption. It never stops. It never collapses. It never picks one outcome. If you trust the equation and nothing else, you get branches. Every other interpretation of quantum mechanics, Copenhagen, pilot wave, objective collapse, cubism, starts with the same equation and then adds a rule or a mechanism or a philosophical constraint to get rid of the branches the equation produces. Carroll's point is that the burden runs the wrong direction. You do not need a reason to believe the branches exist. They are the default output. You need a reason to believe they do not, and no one has produced one. Not a single interpretation that removes the branches can do it without adding an assumption that is not in the math. Copenhagen adds the collapse postulate. Objective collapse adds a new physical mechanism that has never been observed. Pilot wave adds hidden variables and a guiding equation. Each one graphs something onto the Schrödinger equation to force a single outcome. Everett graphs nothing. He trusts the equation as written and accepts what it produces. The branches are not a hypothesis requiring proof. They are a consequence requiring disproof. And in 70 years, no one has disproved them. Not because no one tried, because every experiment designed to find the edge of quantum mechanics, to locate the point where superposition fails and the classical world takes over, has pushed that edge further out instead. The branches keep surviving every test. The equation keeps doing what it has always done. We keep looking for a reason to ignore it. But if the branches are real, why do they look like worlds? Why do you get a stable room with solid walls and a definite floor instead of a smeared out fog of every possible configuration bleeding into every other? The answer is in the seams. When a quantum system decoheres, when the information about its superposition bleeds out into the environment, it does not leak evenly. It leaks along specific lines. Certain combinations of states are more stable than others. They resist the bleeding. They hold their shape while everything around them dissolves into noise. Zurek called this process einselection, short for environment-induced superselection, and it is the reason reality has texture instead of static. Think of a sheet of glass hit by a stone. The glass does not shatter into dust. It cracks along lines of structural weakness, lines where the molecular bonds are slightly weaker than their neighbors. The result is not random. You get shards with clean edges, definite shapes, recognizable pieces. Einselection does the same thing to the quantum state of the universe. When decoherence spreads the information outward, the superposition does not dissolve into an even blur. It fractures along the lines of minimal information exchange between subsystems. The states that survive are the ones that leak the least into their environment. The states that leak the most dissolve first. What remains are branches. Stable, self-consistent, internally coherent branches that look like worlds, because they are the configurations that hold together under the pressure of environmental interaction. You do not see a blur because blurs are unstable. They cannot persist. They dissolve the moment they touch anything. What persists is structure, clean edges, definite outcomes. The world looks solid and definite not because the quantum weirdness stops at some border between the small and the large. It looks solid because solidity is the only thing that survives decoherence. Everything else shatters and the shards that remain have edges so clean you mistake them for the whole. The branches are not chaos. They are the only shapes that hold. So the branches hold. They are stable. They are real. And decoherence separates them so thoroughly that you cannot see from one into another. But the separation is not perfect. In 1982, two physicists named Marlon Scully and Kai Druhl designed an experiment that should not have worked. They took the standard double-slit setup, the one where a particle goes through both slits and produces an interference pattern on the screen. Then they added a detector at each slit. The detector records which slit the particle passes through. The moment you know which path the particle took, the interference pattern disappears. This is standard quantum mechanics. Information about the path destroys the superposition. The particle stops going through both slits and picks one. The pattern on the screen turns into two simple bands. No interference, no mystery. Scully and Druhl added a second step. After the detector records the path information, they erase it. Not hide it, not ignore it, physically destroy the record. And when the record is destroyed, the interference pattern comes back. The particle behaves as though it went through both slits again, as though the measurement never happened, as though the branch that split off when the detector fired has rejoined the branch it split from. Kim and colleagues confirmed this experimentally in 2000. The result is exactly what it looks like. The branches are not welded shut. They can be reopened. If you remove the information that separated them, the separation reverses. The wall between the branches is not made of stone. It is made of information, and information can be erased. You deleted the record of the choice, and the choice stopped existing. Not the memory of the choice itself. The particle did not remember going through one slit and then get rerouted. It went through both again, because the information that forced it to choose had been pulled out of the universe. The wall between the branches is thinner than you think. And the wall does not just have gaps, it has a direction problem. In 1978, John Archibald Wheeler, the same man who supervised Everett's thesis, proposed an experiment so unsettling that it took nearly 30 years before anyone could build it. He called it the delayed choice experiment. The setup is a variation of the double slit. A particle is fired at two paths. At the end of the paths, after the particle has already passed through, you decide whether to measure which path it took or to erase that information and let the interference pattern form. You make this decision after the particle has completed its journey, after it has already either gone through one path or both, and the result matches your choice. If you decide to measure, the particle went through one path. If you decide to erase, the particle went through both. The decision you make now determines what the particle did then, not what it appears to have done, what it actually did. The experiment was realized by Vincent Jacques and his team in 2007. The results confirmed Wheeler's prediction exactly. A choice made in the present reaches backward and reshapes an event in the past. You need to sit with that for a moment. This is not a reinterpretation of data. This is not a matter of perspective. A physical event that has already occurred changes its nature based on a decision that has not been made yet at the time the event happens. The future is reaching into the past and rewriting it. Not in theory. In a laboratory, with photons and beam splitters and detectors and peer-reviewed papers, and a result that has been replicated by independent teams on 3 continents. The branches do not just leak into each other across space, they leak across time. A decision in one branch can retroactively alter what happened in another. The wall between the branches is not only thin, it does not respect the direction you think time moves. If the branches leak across space and across time, is there a way to catch them in the act? Not after the fact. Not by erasing information and watching the pattern rebuild. But in real time, while the superposition is still open, while the particle is still in both states, before anything has been decided. In 1988, a physicist named Yakir Aharonov, working with David Albert and Lev Vaidman, figured out how to do it. They called the technique weak measurement. Standard quantum measurement is violent. You hit the system with enough energy to force a definite answer, and the superposition shatters. You get your result, but you destroy the thing you were looking at. Aharonov's method is different. You touch the system so gently that it barely notices you were there. The interaction is so slight that any single measurement gives you almost no information, just a whisper. But if you repeat the whisper thousands of times across thousands of identical systems, the whispers accumulate into a signal. And the signal shows you something no one had ever directly seen before. It shows you the superposition while it is still alive, before the particle is chosen, before decoherence has spread the information, before the branch has split. And what the signal shows is exactly what the equations predicted. The particle is in both states. Not approximately, not statistically, both, at the same time, with measurable weight in each. You are not inferring this from the interference pattern after the fact. You are watching it happen. You are looking at reality before it has made up its mind. Aharonov's group went further. They showed that weak measurements could reveal properties of quantum systems that had no classical analog at all. Values that lay outside the range of possible measurement outcomes. A spin measurement that returned a value of 100 when the only possible results were +1 and -1. These are not errors. They are signatures of the branches pressing against each other, overlapping in the instant before decoherence drives them apart. You are not seeing one state or the other. You are seeing the interference between states that are about to become separate worlds. You are watching the branches form. And now bring that back to where we started. Every experiment described in the last 10 minutes works on single photons. Tabletop setups, lasers and beam splitters and mirrors bolted to an optical bench in a university basement. The energies involved are tiny. The particles are light. The effects are real, but they are fragile, confined to systems so small and so carefully isolated that the rest of the world never notices. CERN is not a tabletop. The Large Hadron Collider smashes protons together at energies that have not existed in this universe for 13.8 billion years. At those energies, the rules change. Decoherence still operates, but the systems are so energetic and so compressed that the window between superposition and decoherence narrows to almost nothing. The branches have less time to separate. The wall between them is thinner at high energy than it is at low energy. And the anomalies the detectors have been catching since the early 2020s sit exactly in that window. The B meson tilt, the CP asymmetry that outgrew its container, the bumps that flicker at the same energies in two independent detectors. Every one of them involves particles behaving as though more than one version of the outcome is pressing against the measurement at the same time, as though the branches at the moment of collision have not fully separated, as though the wall at those energies is thin enough for something on the other side to leave a mark on the data. The quantum eraser showed you that branches can rejoin when information is destroyed. The delayed choice experiment showed you that branches leak across time. The weak measurements showed you the branches forming in real time. CERN is the only machine on Earth that operates at energies where all three of those effects scale up from single photons to the conditions of the early universe. The anomalies are not glitches. They are not statistical noise that will wash out with more data. They are what branches look like when the wall between them gets thin enough for your instruments to notice. You have been looking at the wall this entire time. You just did not know what you were seeing. But knowing what you are seeing does not tell you why you are seeing it from this side. The branches are real. The wall between them is thin. The data at CERN is starting to show the marks where they press against each other. None of that answers the question that has been sitting underneath everything since the double slit. Who decides which branch you end up in? What picks this version of the outcome and not that one? What determines that you are the version of yourself sitting in this room reading these words instead of the version in the branch next door who made a different choice this morning and is now somewhere else entirely? For 80 years, the most popular answer in physics was, do not ask. Niels Bohr and Werner Heisenberg built that answer in Copenhagen in the late 1920s, and it became the default position of an entire field. The Copenhagen interpretation does not tell you what happens when no one is looking. It tells you the question is meaningless. Reality, according to Bohr, does not have a definite state until it is measured. Before measurement, there is no particle in a position. There is no spin pointing up or down. There is nothing to talk about. The math gives you probabilities, and the measurement gives you a result, and the gap between the two is not a mystery to be solved. It is a boundary you are not allowed to cross. Shut up and calculate. That phrase was never actually said by Bohr or Heisenberg, but it captured the spirit so precisely that it stuck to Copenhagen like a brand. And it worked. For decades it worked. Physicists used the recipe without asking what was cooking. They plugged numbers into the Schrödinger equation, extracted probabilities, compared them with experiments, and collected Nobel Prizes. The question of what was actually happening between measurements was not forbidden because it was dangerous. It was forbidden because it was unnecessary. The recipe produced correct results. Why risk breaking it by asking what it meant? The problem is that the recipe has started giving answers it was never designed to handle. The recipe breaks when you point it at itself. In 1961, a Hungarian-American physicist named Eugene Wigner took the Copenhagen logic and ran it one step further than Bohr ever intended. He imagined a friend inside a sealed laboratory performing a quantum measurement. The friend measures a particle and gets a definite result. Spin up. From inside the lab, the experiment is over. The particle has a state. Reality is settled. But Wigner is outside the lab. He has not opened the door. He has not looked at the result. According to Copenhagen, a system that has not been measured does not have a definite state. The friend, the particle, and the entire laboratory are a quantum system that Wigner has not yet observed. So, from Wigner's perspective, the friend is in superposition. The friend has both seen spin up and seen spin down. The friend is in two states at once, and neither one is real until Wigner opens the door. Now you have a contradiction. The friend says reality is definite. Wigner says it is not. Both are applying the same rules. Both are correct within their own framework. And there is no way to resolve the disagreement without answering a question that Copenhagen explicitly forbids. When does the measurement actually happen? Who counts as an observer? The friend observed the particle. Does that collapse the state? Or does Wigner need to observe the friend? And if someone else needs to observe Wigner, the chain extends another link. Observer observing, observer observing, observer. It does not terminate. There is no final observer. There is no place in the chain where you can plant a flag and say, here. This is where reality becomes definite. Everything before this point was uncertain, and everything after is settled. You cannot find that point because it does not exist. The Copenhagen recipe gave physicists permission to ignore this problem for 60 years by restricting the questions they were allowed to ask. Wigner proved that the restriction was not a feature of the theory. It was a crack papered over with a rule that said, stop looking. In 2019, a team of physicists stopped ignoring the crack and built the experiment. Massimiliano Proietti and his colleagues at Heriot-Watt University in Edinburgh constructed a real version of Wigner's thought experiment using entangled photons. Not a simplified analog. Not a mathematical approximation. A physical system where two observers could make measurements on the same quantum event and compare results. The setup used 6 entangled photons routed through a network of beam splitters and wave plates. One pair of photons acted as the system being measured. 2 observers, implemented as parts of the optical circuit, each performed a measurement on the system from their own reference frame. The results were recorded independently and compared. The finding was exactly what Wigner's logic predicted. The 2 observers obtained results that directly contradicted each other. Not in the sense that they measured different values. In the sense that their measurements were logically incompatible. One observer's result could only be true if the other observer's result was false, and both results were physically valid. Both were produced by legitimate measurements on real photons following real quantum mechanics. Neither could be dismissed as an error. You are not dealing with a matter of interpretation. You are not dealing with 2 people reading the same data differently. You are dealing with a physical experiment in which 2 measurement devices, operating on the same quantum event, produce outcomes that cannot both be true in a single shared reality. The most straightforward reading of this result is that there is no single shared reality. The 2 observers are not disagreeing about one world. They are each correctly describing their own branch. And the branches are incompatible. Proietti's experiment did not prove that objective reality does not exist. What it proved is narrower and more precise. It proved that if quantum mechanics is correct, and if the measurements are valid, then the assumption that all observers share a single, consistent account of physical events cannot be maintained. The observers are right, both of them. That is the problem. If two observers in the same laboratory cannot agree on what happened to the same photon, what happens when you scale this up? Not to two people in a room, to everything. The entire universe is a quantum system. It contains every particle, every field, every interaction that has ever occurred or will ever occur. If quantum mechanics applies to individual photons and entangled pairs and laboratory setups, it applies to the whole structure. There is no reason it would stop. There is no size limit written into the equations. And if the whole universe is a quantum system, then the question Wigner asked about his friend applies to the cosmos itself. Who observes the universe? There is no one outside it. There is no door to open. There is no Wigner standing in the hallway, waiting to collapse the state. In 1967, two physicists confronted this problem directly. John Wheeler and Bryce DeWitt wrote down an equation that describes the quantum state of the entire universe. It is called the Wheeler-DeWitt equation, and it is one of the strangest objects in physics. Not because the math is unusually complex, because of what the math does not contain. The equation has no variable for time. The letter T does not appear. The most complete quantum description of the universe, the equation that should contain everything, does not contain the one thing you feel most certain about: the passage of time. It describes a static object, a structure that does not evolve, does not change, does not move from one moment to the next, and it has no observer. If collapse requires an observer, and the universe has no external observer, then the universe has never collapsed. The wave function of the cosmos has never snapped into a single state. It is still in superposition. Every possible configuration of matter and energy, every possible history, every possible version of every event that has ever occurred, coexisting inside a single mathematical object that does not know what time is. You are inside that object. You are not observing it from outside. You are a pattern within it. A pattern that generates the sensation of time, the sensation of definiteness, the sensation of being in one place at one moment, from inside a structure that contains all places and all moments simultaneously. The universe never decided. You are living inside the indecision, but you feel like it decided. You feel a direction. Yesterday is behind you and tomorrow is ahead, and the arrow only points one way. If the universe is a frozen block with no time variable in its deepest equation, where does that arrow come from? Every fundamental law of physics is symmetric in time. Run Newton's equations backward, and the planets trace the same orbits in reverse. Run Maxwell's equations backward, and the electromagnetic waves converge instead of spreading. Run the Schrödinger equation backward, and the quantum states evolve in reverse just as smoothly as they evolve forward. None of them know the difference between past and future. None of them care, except one. In the 1870s, an Austrian physicist named Ludwig Boltzmann formalized a rule that every other law of physics ignores: the second law of thermodynamics. It says that entropy, the measure of disorder in a system, increases over time. A glass shatters on the floor. The pieces do not reassemble. Cream poured into coffee spreads. It does not unpour. A fire burns wood into ash. The ash does not unburn. Every irreversible process you have ever witnessed is the second law in action. It is the only law in all of physics that distinguishes past from future. The only one. Every other equation runs the same in both directions. The second law plants a flag in one direction and says, "this way." And that flag is the only reason you experience time as having a direction at all. Your memories form because neural connections are thermodynamic processes that increase entropy. Your body ages because metabolic reactions are thermodynamic processes that increase entropy. The arrow of time is not a feature of the universe. It is a feature of one law. One rule out of all the rules that physics has ever written. Everything you feel about the passage of time, every intuition about past and future, every sense that you are moving forward through something, rests on a single thermodynamic inequality. One law. Holding up your entire experience of reality, alone. And that law has a problem. The second law says entropy increases. Disorder grows. Systems move from ordered to disordered. That explains the direction. But it does not explain the starting point. If entropy always increases, it must have been lower in the past. And if you follow that logic all the way back, entropy at the very beginning of the universe must have been extraordinarily low, extraordinarily ordered, a state of almost perfect smoothness, almost perfect uniformity, the kind of initial condition that would produce a cosmos capable of generating stars, planets, chemistry, and eventually you. Roger Penrose calculated the probability of that initial condition. The number he produced is not like other numbers in physics. It is not a large number that you can compare to familiar things. It is a number so extreme that the act of writing it down exceeds the physical capacity of the universe. 1 divided by 10 to the power of 10 to the power of 123. If you tried to write that number in ordinary notation, with a 1 followed by zeros, you would need more zeros than there are particles in the observable universe. Not more than the stars, not more than the atoms, more than the particles. There is not enough matter in existence to store the digits. The probability of the universe beginning in the state it began in is so small that the word improbable does not apply. Improbable means unlikely but possible. This number is so far past unlikely that it sits in a category that does not have a name. And yet, here you are. The entropy was low. The arrow of time exists. You are sitting in a universe that started in the single, most statistically absurd configuration imaginable, and nobody can tell you why. The second law explains why time flows forward from that starting point. It does not explain why the starting point was there. You have an arrow. You do not have a bow. The arrow flies. Nobody drew it back. For over a century, physicists have treated that starting point as a given. The universe began in a low entropy state. Accept it and move on. In the early 2000s, 2 philosophers of physics named David Albert and Craig Callender gave this acceptance a name. They called it the past hypothesis. Not a law, not a derivation, not a consequence of deeper physics. A hypothesis, a postulate, something written into the foundations by hand because without it nothing else works. Albert put it bluntly. The past hypothesis is not something we derived from the equations of motion. It is something we added to them because the equations of motion alone do not tell you which direction time goes. They work perfectly in both directions. They are as happy running the universe backward as forward. The only reason you see entropy increasing, the only reason cream spreads through coffee and not the reverse, is that someone set the initial condition to be absurdly ordered and then let the math run. But nobody set it. That is the point. There is no mechanism in physics that produces a low entropy beginning. There is no law that requires it. There is no equation that predicts it. The starting condition of the universe is not explained by physics. It is assumed by physics. The entire arrow of time, every memory you have, every sense that yesterday happened before today, rests on a single assumption that was inserted into the framework, because without it the framework could not reproduce what you see when you look around. Physicists did not solve the problem of why time flows forward. They wrote the answer on a piece of paper, slid it under the equations, and agreed not to look underneath. The arrow of time is not a discovery. It is a patch, a placeholder where an explanation should be. And for 100 years the placeholder held because nobody could think of anything better. Then, someone did. What if the arrow does not come from the beginning? What if it comes from the branching? In 2017, a physicist named Lev Vaidman, the same Vaidman who helped develop weak measurements, published a paper arguing that the direction of time is not a consequence of low initial entropy. It is a consequence of the universe splitting. Every quantum event that has more than one possible outcome produces branches. The number of branches increases with every interaction. Particles collide and the outcomes multiply. Atoms decay and the tree grows wider. The universe does not move from past to future. It moves from fewer branches 2 more branches. And that is the arrow. Not entropy climbing upward from an improbable floor. Branching. Spreading outward from every quantum event like cracks propagating through a windshield. Janay and Ismail, a philosopher of physics at Columbia, extended this argument into a full framework. If the branching is real, then entropy increase is not the cause of the arrow. It is a side effect. Entropy increases because the number of branches increases, and more branches means more possible configurations. And more possible configurations is what entropy measures. The low entropy beginning stops being a mystery. It is low entropy because the universe had not yet branched. The tree had not yet grown. The trunk is narrow not because someone carved it that way, but because it had not had time to split. You have been thinking of time as a river flowing from a source. Weidmann and Ismail say it is a tree growing from a seed. The river needs someone to explain where the water comes from. The tree does not. The tree grows because growing is what trees do. Each fork creates 2 paths, and each path forks again, and the direction you experience as forward is simply the direction in which there are more forks. You are not moving through time. You are riding the expansion of a structure that cannot stop splitting. The sensation of the present is the feeling of being at the newest fork. The sensation of the past is the feeling of knowing which forks are behind you. The sensation of the future is the feeling of not knowing which fork comes next. Time is not a river. Time is branches multiplying, and you are at the tip. If quantum mechanics says reality branches at the smallest scale, and if that branching explains the arrow of time, then you might expect the effect to be confined to the quantum world. Particles splitting, atoms forking, tiny events producing tiny branches too small to matter at the scale of stars and galaxies. Cosmology says otherwise. In 1986, a Soviet-American physicist named Andrei Linder proposed a model of the early universe called eternal inflation. Standard inflation theory says the universe expanded exponentially in the first fraction of a second after the Big Bang, then slowed down, then settled into the expansion rate you see today. Linder's version says the inflation never stopped. Not everywhere. In most of the universe, the exponential expansion is still happening right now. Stretching space faster than light can cross it. But in scattered pockets, the inflation slows. Energy converts into matter. Physics settles into stable patterns. A pocket universe forms. Ours is one of those pockets. A bubble of calm inside an ocean of expansion that has been running for 13.8 billion years and will run for eternity. Each pocket can have different physical constants, different particle masses, different force strengths. The speed of light in one pocket does not have to match the speed of light in another. The rules are local. They solidified when the pocket formed, the way crystals form different patterns depending on the temperature and pressure at the moment of crystallization. 2 branches of physics, quantum mechanics and cosmology, built by different people using different math to describe different scales, arrived at the same conclusion independently. Reality branches. At the quantum level, it branches through superposition and decoherence. At the cosmological level, it branches through inflation and pocket formation. The mechanisms are different. The math is different. The scales are separated by 60 orders of magnitude. The answer is the same. There is more than one version of everything. How many versions? Leonard Susskind, a theoretical physicist at Stanford who helped create string theory, calculated the number of possible universes that the landscape of string theory allows. String theory describes the fundamental constituents of reality as tiny vibrating strings, whose behavior depends on the geometry of extra dimensions curled up at scales too small to observe directly. The geometry can take different shapes. Each shape produces a different set of physical laws, different particle masses, different force strengths, different constants. Susskind counted the shapes. The number he arrived at is 10 to the power of 500. That is not a large number in the way that a billion is a large number. A billion you can picture. A billion seconds is roughly 32 years. 10 to the 500 is a number that breaks all analogies. If every atom in the observable universe were itself a universe containing as many atoms as our universe, and every one of those atoms were also a universe, and you repeated this nesting 100 times, you would still not reach 10 to the 500. Each of those configurations is a mathematically self-consistent set of physical laws. Each one produces a universe that works. Particles form, forces operate, structures emerge. Not all of them produce stars. Not all of them produce chemistry. Not all of them produce anything you would recognize. But they work. They run. They are valid solutions to the same underlying equations. Your universe, with its specific electron mass, its specific gravitational constant, its specific speed of light, is one configuration out of 10 to the 500. Not chosen, not designed, not optimized. One point on a landscape so vast that the word vast is meaningless applied to it. You are not in a special place. You are in a place. The obvious response is, so what? You are here. You exist. Your universe has the right constants for stars and carbon and water and DNA. Out of 10 to the 500 possibilities, this one works for you. That is not a coincidence. It is a selection effect. If the constants were different, you would not be here to notice. This argument has a name: the anthropic principle. Brandon Carter formulated it in 1973. Steven Weinberg used it in 1987 to predict the approximate value of the cosmological constant. It sounds like an explanation. It feels like an answer. You are here because you could not be anywhere else. The universes where the constants do not support observers do not contain observers asking why the constants are right. The ones that do contain observers, and those observers inevitably find that the constants support their existence. Case closed. Except, it is not closed. The anthropic principle tells you why you are not surprised. It does not tell you why this configuration exists. Saying you can only observe a universe compatible with your existence does not explain why a universe compatible with your existence is present in the first place. It is like standing in a room that happens to be the only room in the building with oxygen, and saying, I am here because this is the only room I could breathe in. That accounts for your location. It does not account for the room. It does not tell you who built it, or why, or whether it was built at all or arrived by chance. The anthropic principle is not an answer. It is the shape of the hole where an answer should be. Physicists have been circling this hole for 50 years, measuring its edges, naming its features, publishing papers about its depth. None of them have filled it. The question is still open. Why this branch and not another? And there is one place on this planet where the question might stop being open. The two types of branching, quantum and cosmological, were discovered by different fields using different equations at different scales. Quantum branching happens at the level of particles. Cosmological branching happens at the level of universes. 60 orders of magnitude separate them. They should have nothing to do with each other. But they produce the same structure: branches, forks, multiple versions of reality coexisting within a single framework. If that is a coincidence, it is the largest coincidence in the history of science. If it is not a coincidence, then somewhere between the quantum scale and the cosmological scale, there is a point where the two types of branching connect. A seam. A place where the fork in the particle and the fork in the cosmos are the same fork. Finding that seam requires energy, not the energy of a tabletop laser or a university laboratory. Energy dense enough and concentrated enough to push quantum effects to the edge of the scale where cosmological structure begins. There is one machine on Earth that operates at those energies. The Large Hadron Collider at CERN pushes protons to energy densities that existed only in the first microseconds after the Big Bang. That is not a quantum scale. That is not a cosmological scale. That is the boundary between them. The anomalies that started this entire conversation, the B meson tilt, the CP asymmetry that keeps growing, the bumps that flicker at the same energies in two independent detectors, they all sit at that boundary. They all involve particles behaving as though the wall between branches is thin enough to leak. You have now circled back to CERN for the second time. The first time you understood that the anomalies might be traces of branches pressing against each other. Now you understand something more. CERN does not just sit at the boundary between branches. It sits at the place where two kinds of branching might be one. That brings you to the deepest layer. Beneath the particles and the forces and the branches, beneath the equations that describe them and the experiments that test them, there is a question about what reality is made of. Not what it contains, what it is. In 1961, a physicist at IBM named Rolf Landauer proved something that should have changed the way everyone thinks about the universe. He proved that information is physical, not information in the abstract sense, not data as a concept, physical information. Landauer showed that the act of erasing a single bit of information, flipping a 1 to a 0 with no record of what it was before, requires a minimum amount of energy. The energy is tiny. It is proportional to the temperature of the environment times Boltzmann's constant times the natural logarithm of 2. But it is not 0. It cannot be 0. Erasing information produces heat. Storing information requires space. Processing information takes time. Information obeys thermodynamics the same way matter does. It has weight in the sense that it affects the energy balance of any system that contains it. It has temperature in the sense that its erasure warms the environment. It has entropy in the sense that losing track of it increases disorder. You have been thinking of information as something that describes reality. A label you attach to a particle. A measurement you write in a notebook. Landauer proved that the label is as real as the particle. The measurement is as physical as the thing being measured. When the quantum eraser experiment destroyed the record of which slit the photon passed through, it did not just change what you knew. It changed the physical state of the system. The information was not a description of reality sitting outside the experiment. The information was part of reality. And removing it changed what reality did. If information is physical, then what is more fundamental? The matter or the information? John Archibald Wheeler spent the last 2 decades of his life arguing that the answer is information. Wheeler was not a marginal figure. He named the black hole. He supervised Everett's thesis and Feynman's thesis. He worked on the Manhattan Project. He was one of the most influential physicists of the 20th century. And in the 1990s, he proposed a principle so simple it fits on a bumper sticker. It from bit. Every particle, every force, every physical quantity in the universe derives its existence from binary choices. Yes or no. Spin up or spin down, here or there. The material world is not the foundation with information written on top. The information is the foundation with the material world emerging on top. Think of it this way. You see a table, solid wood, you can knock on it. It holds your coffee. But the table is made of atoms. The atoms are made of quarks and electrons. The quarks and electrons are described entirely by quantum numbers, discrete values that answer binary questions about spin, charge, position, momentum. Remove the quantum numbers and there is nothing left. No substance underneath. No stuff behind the math. The numbers are the stuff. Wheeler said the universe is not a machine running on a substrate. It is a network of binary answers with no substrate underneath. Every ite, every physical thing, comes from a bit, a binary piece of information. The table exists because certain questions were answered. The coffee exists because certain questions were answered. You exist because a specific set of binary questions, stretching back to the first microsecond, were answered in a specific sequence that led to carbon and water and neurons, and the particular configuration of matter that calls itself by your name. Not answers recorded on some material. Answers that are the material. You are not made of atoms. You are made of answers. If reality is built from information, then a question that used to sound like science fiction stops sounding fictional. In 2003, a philosopher at Oxford named Nick Bostrom published a paper that did not argue we live in a simulation. That is the version you have heard. That is not what the paper says. What the paper says is simpler and harder to dismiss. Bostrom constructed a trilemma, 3 statements. At least one of them must be true. The logic connecting them is airtight. Statement 1. Virtually all civilizations at our level of development go extinct before they reach the computational capacity to simulate conscious minds. Statement 2. Virtually all civilizations that do reach that capacity choose not to run such simulations. Statement 3. We are almost certainly living inside a simulation. You do not get to reject all 3. The math forces you to accept at least one. If advanced civilizations survive, and if they run simulations, then the number of simulated minds vastly exceeds the number of original minds. If you are a conscious being, and you do not know whether you are original or simulated, the odds overwhelmingly favor simulated. Not by a small margin, by a margin so large that the probability of being original rounds to 0. You might reject statement 3 on instinct. Most people do. But that means you're betting everything on statement 1 or statement 2. Either civilizations reliably destroy themselves before reaching that threshold, or they reliably choose not to use a capability they possess. Neither of those is comforting, neither can be verified, and neither has anything to do with faith or philosophy. This is probability theory applied to a question about the nature of observation, and no one has found an error in the reasoning in over 20 years. 2 of the 3 doors lead somewhere you do not want to go. You have to pick one. But you do not have to pick one if the question dissolves. And this is where the branches come back. If reality is information, and if the universe branches, then every concept you have struggled with in the last hour maps cleanly onto a single framework. Superposition is not a particle being in 2 places at once. It is a computation running 2 processes in parallel. The double slit is not mysterious. It is a system evaluating both paths simultaneously and producing a combined output. Decoherence is not a mysterious collapse triggered by observation. It is resource management. The system tracks every interaction. When the information about one branch spreads into too many environmental variables, the cost of maintaining coherence between branches exceeds the benefit. The system lets them diverge. It stops tracking the correlation. Not because something physical happened, because continuing to track it would consume more information than the result is worth. The observer is not a conscious mind peering at a particle. The observer is the moment when the system commits resources to one branch and deallocates the other. You are not a user sitting outside the program watching it run. You are a process inside the program. A subroutine that generates the experience of continuity, the experience of time, the experience of being a single self in a single world, because that is what the architecture of decoherence produces. A process that can only read its own thread. Every anomaly in quantum mechanics becomes expected behavior when you describe reality as a system managing information under constraints. The quantum eraser works because deleting a record of which path was taken removes the flag that told the system to split the threads. The delayed choice experiment works because the system does not finalize the branch assignment until all the relevant information has been committed. The weak measurement works because you can sample a thread without forcing the system to commit. CERN works at energies where the thread management breaks down, where the flags blur, where the system is processing so much information in such a compressed space that the boundaries between threads start to leak. You are not watching the universe from outside. You are a thread inside a system that is deciding, right now, which threads to keep running. And that reframes everything you thought you knew about the wall. You have been thinking of decoherence as a limitation, a barrier your technology has not yet broken through, a wall between you and the other branches that better instruments, higher energies, smarter experiments will eventually let you cross. Zurek's work on einselection says something different. Einselection is not a limitation. It is a filter. It selects the states that can persist. Out of an infinite number of possible quantum configurations, most are unstable. They fall apart the instant they interact with anything. They cannot hold a shape. They cannot sustain a pattern. They cannot support structure of any kind. Ein selection strips those away. What survives is the narrow set of states that resist environmental interaction long enough to become real in the sense that you use the word. Atoms, molecules, tables, stars, you. Without Ein selection, there is no structure. There is no chemistry. There is no time in the sense that you experience it. There is noise. Every possible state of every possible particle existing simultaneously with no hierarchy, no persistence, no difference between one configuration and another. A television tuned to every channel at once is not showing you more information. It is showing you less. Static contains every possible image superimposed into nothing. Ein selection is the tuner. It is the mechanism that pulls a signal out of the noise, and the signal it pulls out is the one you call reality. You have been thinking of the wall between branches as something that keeps you from seeing the full picture. But the wall is the picture. Without it, there is nothing to see. Decoherence is not keeping you from the truth. Decoherence is the only reason there is a truth to keep. It is not a barrier between you and a bigger reality. It is the load-bearing wall of the building you are standing in. Every floor, every room, every structure in the building exists because that wall is intact, and CERN is pressing against it with more force than anything in the history of this planet. That force is not passive. It is not a telescope pointed at a distant star. It is not a microphone picking up a faint signal. Measurement at the energy CERN operates at is not observation. It is contact. In 1958, Lev Landau and Evgeny Lifshitz, two Soviet physicists whose textbook series became the foundation of theoretical physics education for half a century, formalized a principle that most people outside physics have never heard. Measurement is irreversible. When you measure a quantum system, you do not passively read its state. You interact with it. You change it. You entangle your measuring device with the system being measured, and that entanglement cannot be undone. The information you gained is not a copy. It is a link, a physical connection between your instrument and the thing it touched. Before the measurement, the system and the instrument were separate. After the measurement, they share information. They are correlated, and that correlation is permanent. You cannot unmeasure. You cannot put the information back. The system has been altered by the act of knowing about it, and the alteration propagates outward through every subsequent interaction like a ripple that never dampens. Now, think about what CERN does. It does not measure particles the way a thermometer measures temperature. It smashes protons together at energies that recreate the conditions of the first microsecond. It creates particles that have not existed for 13.8 billion years, and it measures them. It entangles its detectors with the products of the collision. If those products include traces of other branches, if the anomalies are what they appear to be, then CERN has not observed the wall between branches. It has touched it. It has entangled our instruments with something on the other side. And that entanglement, according to Landau and Lifshitz, cannot be undone. You did not look through a window. You opened a door. You cannot close it because closing it would require destroying the information you gained, and the information has already spread into the detectors, into the computers, into the papers, into this sentence. The connection is made. It does not unmake. So here is where you stand. The equations say the branches are real. 70 years of experiments have failed to find the edge of quantum mechanics. Every test designed to locate the boundary where superposition stops and the classical world begins has pushed that boundary further out instead. The branches are not a fringe interpretation. They are the default output of the most tested equation in the history of science. Decoherence separates them. Ein selection stabilizes them. The wall between them is not a limitation of your instruments. It is the mechanism that makes reality coherent. Without it, there is no structure, no atoms, no time, no you. And CERN, operating at energies that have not existed since the first microsecond of the universe, is pushing against that wall harder than any machine ever built. The anomalies in the data are not noise. They are not statistical fluctuations that will wash out with more collisions. They are what the wall looks like when it gets thin. The B meson tilt, the CP asymmetry that has been growing for 60 years, the bumps that flicker and return at the same energies in independent detectors. Every one of them sits at the boundary where decoherence weakens, where the branches have not fully separated, where something on the other side leaves a mark that your instruments can almost read. The quantum eraser showed you that branches can rejoin when information is destroyed. The delayed choice experiment showed you that branches leak across time. The weak measurement showed you that branches forming before decoherence drives them apart. Proietti showed you that two observers inside the same experiment can see incompatible realities. Wheeler and DeWitt showed you that the universe itself has never collapsed into a single state. And Zurek showed you that the wall holding everything together is not a barrier to knowledge. It is the load-bearing structure of reality itself. You did not set out to find this. You set out to test a model of particle physics. You ran collisions. You checked predictions. And the predictions started drifting. You followed the drift, and it led you here. To a wall that is not supposed to be thin. To data that should not exist. To a connection between your instruments and something on the other side that cannot be severed because measurement is irreversible and the information has already spread. You are not explorers standing at the edge of new territory. You are a crack in a structure that holds everything together. A crack that formed because you looked too hard at the place where the seams are thinnest. And every collision at CERN, every run, every year of data, every decimal place of precision, pushes the crack a little wider. Not because the machine is powerful, because the act of knowing is itself the damage. The wall does not care about your intentions. It does not distinguish between curiosity and destruction. It only knows that information has crossed from one side to the other, and that crossing, according to every principle of quantum mechanics, is permanent. The crack does not heal. It has never healed. It has, and you are still running the machine. But step back for a moment. Breathe. Everything you have just heard is a model. Every equation, every interpretation, every framework that describes branches and walls and cracks is a human construction built to make sense of data points on a screen. The data is real. The math is real. The anomalies are real. But the story we wrap around them is ours. We built it the same way we build every story, out of pattern recognition and metaphor, and the deep human need to make the incomprehensible feel like something we can hold in our hands. The universe does not owe us a shape we can understand. It does not owe us an answer that fits inside a sentence. It does not even owe us the comfort of knowing whether the wall is real, or the branches are real, or the crack matters. What it owes you is nothing. And that is not a tragedy. That is the point. You are a specific configuration of matter, sitting in a specific location, in a specific branch of whatever this structure turns out to be. You are not an abstraction. You are not a probability cloud. You are not a thread in a system waiting to be deallocated. You are a person who breathes and eats and forgets where they put their keys and laughs at things that are not that funny and lies awake, sometimes wondering if any of it means anything. And here is what the physics actually tells you, underneath all the horror and all the math. Out of every possible arrangement of matter, out of every branch and every fork and every quantum event that could have gone a different way, this specific configuration exists. The one that contains you. Not a version of you. You. The one hearing these words right now. The probability of your exact configuration is so small that it makes Penrose's number look generous. And yet, here you are. Not because the universe chose you. Not because a simulation selected you. Not because an observer collapsed a wave function in your favor. You are here because the structure of reality, whatever it is, permits you. And that permission is not something you need to earn or justify or understand. It is something you already have. Every branch of physics we explored tonight, from the collider to the block universe to the branches to the wall, All of it describes a structure so vast and so indifferent that your existence inside it should be impossible. But you are not impossible. You are actual. You are the part of the structure that woke up and asked what the structure is. And no equation, no matter how complete, will ever be more remarkable than the fact that something inside the math learned how to ask about the math. The branches may be real, the wall may be thinning, the crack may be growing. None of that changes the fact that right now, in this specific slice of this specific branch, you are here. You are conscious. You are thinking about what you just heard. And that means this branch, whatever else it is the one where someone is paying attention. The universe is vast and possibly branching and possibly computing and possibly indifferent to everything inside it. But you are not indifferent. You care. You wondered. You stayed until the end. And in a structure that may contain every possible version of every possible outcome, the version that contains someone who cares is the one worth being in. Do not be afraid of the wall. Do not be afraid of the branches. Do not be afraid of the crack. Be the thing that the structure cannot produce on its own. Be the part that notices. Be the part that asks. The equations will keep running whether you understand them or not. The collider will keep firing. The data will keep arriving. The wall will do whatever the wall does. But none of it has meaning until someone stands inside the structure and decides that it matters. You are that someone. That has always been enough,